Hey everybody. Tonight we're going to do some more work with absolute value inequalities, and we're going to take a look at where we might see problems like this arise in a real-world type situation. In our first example, you're buying a new computer and find 10 models in a store advertisement. The prices are, etc. You are willing to pay the mean price with an absolute deviation of at most $100. Write and solve an absolute value inequality to find out how many of the computer prices meet your condition. So let's go through our process here, our STAR process. We want to study the problem, underline what we're looking for. We want to find how many of the computer prices meet our condition. Now, the information we need is the prices of the computers. Obviously, we'll box all of that information. And we also need to understand that we are willing to pay the mean price, and we know that the absolute deviation is at most $100. Now, this problem doesn't tell us what the mean price is, so that's actually something we're going to have to figure out on our own. To find the mean, we have to find the total. We add all of the numbers together, and then we divide by how many numbers there are. So we have to do 890 plus 750 plus 650 plus 370 plus 660, I might run out of room, plus 450 plus 650 plus 725 plus 825, and we take that total and we divide it all by 10 because there are 10 computers. When we add all of those numbers together, we get 6,640. So we got 6,640 divided by 10 is 664. So this is our mean price. Okay, that's something we need. So remember, in an absolute deviation problem, that's what kind of problem we're looking at here, absolute deviation, we say that the difference or the distance between the possible numbers that we're looking for, which we represent with x, and the ideal number, which is 664, equals what the absolute deviation is, or in this case, is less than or equal to the absolute deviation. The reason we use less than or equal to here is because it says the absolute deviation is at most $100, meaning that the distance between x and 664 could be $0, right? We'd be willing to pay 664. It could be $10. We'd be willing to pay 10 more or 10 less, all the way up to 100 more or 100 less. So remember, when we set these up, what these represent, x are the possible values, 664 in this case is the ideal value. That's what we're willing to pay. And 100 is the deviation. How much could be above the ideal number or below the ideal number. Now, to solve this inequality, we're going to have to rewrite it. So I can rewrite this as a compound inequality. Since this is less than or equal to, this is going to be an AND inequality. So we have x minus 664 is less than or equal to 100. It is also greater than or equal to negative 100. And we can think about what this means. This distance between the possible price and the ideal price could be positive 100, meaning x could be $100 more, or the difference could be negative 100, which means x would be $100 less. And now we can solve this just by adding 664 to both sides. Plus 664. This gives us 564 less than or equal to x, which is less than or equal to 764. So here we have a statement that lists all of our possible values of x. X is between 564 and 764. Now, to actually answer the question, how many of these computers would fit within this range, would we actually be willing to buy, we have to look at all of our various prices. So let's scroll back up a little bit here. Our prices that would work include 750, 650, 660, 670, 650 again, and 725. So we have 1, 2, 3, 4, 5, 6. 6 of those computers would fit within our given range. In our second example, Stephen is a safety engineer at a hydroelectric power plant. The plant generates power using water pressure, but if the pressure is too high, some of the machinery can get damaged. If it's too low, the plant can't generate any power. The ideal pressure is 8,000 psi, pounds per square inch, with an absolute deviation of at most 15%. Stephen wants to program an alarm system that sounds whenever the pressure is outside of that range. Write and solve an absolute value inequality to find what pressures are outside of that range. So we are looking for pressures, right, that are outside of that range. Now, the big numbers we're going to need 8,000, because that's the ideal pressure, and we're going to need the absolute deviation, 15%. Now, it's 15% of 8,000, so we've got to make sure we find that first. So to find 15% of 8,000, we can use our percent equation. The part equals 0.15, that's the percent, times the base, or the whole, which gives us A equals 1,200 pounds per square inch. So this right here is the deviation, the possible deviation from the ideal number. Now, when we write our absolute value inequality, we have to be very careful about what we're looking for. We know that the absolute value of x minus 8,000 ideally is less than or equal to 1,200, because it says that the deviation is at most 1,200. So this represents what is safe, but we are looking for the values that are outside of that range. So our inequality is actually x minus 8,000 is greater than 1,200. If this is the difference between the actual pressure and the ideal pressure, we want to know when is it outside of that number, when is it bigger than that number. So when we rewrite this equation now, or this inequality, we have x minus 8,000 is greater than 1,200, or x minus 8,000 is less than negative 1,200. And now when we solve these, we add 8,000 to both sides, and we get x is greater than 9,200, or when we add 8,000 over here, we get x is less than 6,800. So he's going to program the alarm to sound when x is over 9,200 psi, or if x is less than 6,800 psi.